Hi, welcome to another lecture on Calculus 3. Today we are going to start a new chapter on multiple integration. First section is going to be on iterated integrals and area in the plane. We are going to go back to Calculus 1 and review some items from there and then come back. So back in Calculus 1 you learned about area between curves. So we are going to start with that same concept and use it to introduce a new terminology and procedure called iterated integrals. So all the integrals you have seen before, there was just one integral involved, and now we are going to go after multiple integration, or sometimes referred to as iterated integrals. So let's go back in Calculus 1. You had a situation, perhaps two curves in a plane, f2 larger than f1, and both continuous functions, and we want to find the area between these two limited by two walls a and b. So we had an approach there, and we are going to essentially rewrite that same formula we had. Sometimes our graph was in a different configuration. Here is x is a function of y. We have two functions. G2 is supposed to be larger than G1, both of them continuous, and we are trying to find the area going from C to D between these two curves, and we want to see that turns out to be the formula I've written down here. So the presence of these integrals gives rise to this concept of iterated integral. Let me explain the ingredients, and then we are going to explain the meaning of them. So f1 and f2 here is a lower and upper function, and then we are integrating with respect to dy first, meaning going from lower to the upper, and then a and b are limits of integrals, or the walls of the integral from left to right. And then there is a secondary integration with respect to x, that we are going in the x direction. In this configuration we have two functions, g2 and g1. g2 is the larger than g1, and both of them are continuous again. In this case we are integrating going in a horizontal fashion first, so that's the inner integral, dx integrated from g1 to g2. And then there is a secondary integral that goes from the lower to upper value of y. So you see an integral with respect to y from c to d. Notice the change in the manner we are writing the variables and the limits of the integral. Okay, there's going to be many versions of this, and when we go to 3 dimension that's going to be even more complicated. So it's essential to understand the notation, be able to write it without getting confused as to what is happening. Due to the presence of multiple possibilities, it's going to be impossible to memorize these kind of things. We need to understand what is involved. So let's go back to Calculus 1. Let's review what we meant by these differentials and practice some simple cases and gradually build up to the concept that we have here. And in that case we can handle iterated integrals. If there are two of them or three of them, it would be possible to do. So step number 1, what did we mean by differential of x, or dx? So we are going to go back to some very basic concepts back in Calculus 1. So dx, let's think about this thing as a displacement on x-axis. So suppose we have x-axis and we go from some location, say x1, to some other location x2. So this displacement can be shown by x2 minus x1. Now when we write something like integral dx from a to b, how can we think about this thing? The way to think about this is, again, go back to the x-axis, and think about these displacements. We starting our displacement or our journey at the location A. We make some displacement, go somewhere, another displacement, and so on until we arrive at the location B. So this integral simply refers to the sum total of all of these displacements. If they start at A and finally they reach B, well, obviously if you start at A and go to B, the total displacement that you have, sum of all the displacement, is simply B minus A. Of course, if you had started your journey from B and then coming to A, so if you're starting at B and now you're making mostly negative displacements, your total displacement now would be A minus B, which turns out to be a negative quantity. Okay, next we had the fundamental theorem of calculus. If I have a function which is just 1 and I ask what is the antiderivative of it, well, antiderivative of 1, what's a function whose derivative is 1? So of course x, and then I might have some constant, any constant, say k. So antiderivative of 1 is x plus k. In other words, if I take a derivative of x plus k, derivative of a constant with respect to x is 0, and derivative of x is 1, of course I get 1 back. Now we said there's a close connection between these two observations. If I have the same integral but made into a definite integral from a to b, I can find this answer by taking my antiderivative and evaluate it at start and end values. So it's going to be b plus k and minus a plus k, and of course we get that b minus a back. So that observation we had here, that this definite integral is b minus a, can also be obtained in this more systematic way. We get the same answer. Now this constant, of course, is a constant of integration, and now if you have multiple integrations to do, each of them can have its own constant. So let's go ahead explain it in a context of going into 2 dimensions. So we started our conversation with x-axis here, and we're just traveling back and forth or just on the x-axis, but we don't have to literally be on the x-axis. So I can start from some place here to some other place here. So if this is a and b, integral of dx for me from a to b, well, still b minus a. And if I was somewhere else here, well, same story. If I still go from a to b, so x is changing from a to b. In the first case, my y value is something. In the second case, my y value is something else. But that is irrelevant to what I'm doing here. My total x displacement is from a to b is always b minus a. Now it doesn't matter what variable I have in my mind, I can do the same thing. So for example, if I choose to go in the direction of y, and so if I go from some value, so this is the c value, so in all of these cases, let's emphasize we are still going from a to b. If I go from c to d, my integral dy from c to d, meaning I am making some displacements starting at c, eventually ending up at d. What is my net displacement? Well, of course, that is d minus c. And again, it doesn't matter what my x is, so long as my y is changing from c to d. So in both of these cases, for this one as well, integral from c to d, so this is going from c to d, this is going from c to d, of dy is d minus c. Okay, so the integral of their differential is simply n value minus starting value. Now we come to the concept of area. So let's go ahead and see what we mean by area. Suppose I go after this simple shape. So at the beginning we are going to start with very simple graphs, and later on we get to it, we are going to have more complicated ones. So this type of simple pictures are referred to as vertically simple in your textbook. So we don't have crisscrosses and breaks and so on. Okay, suppose I want to calculate this this area, the first one that we had on the left here. So this, suppose we are going after that one. So we are situated in a coordinate system, and I want to get a handle on this area. What can I do? So what the idea that you learned in Calculus 1 was to break it up into strips. So I make this into these type of strips. Calculate the area of each strip. So I'll have lots of these strips. Calculate the area of each of them and add them up. Well, these are almost like rectangles. The base of these rectangles, that's going to be that differential of x we were looking at. The height of these two rectangles, well, whatever height is at this location minus the height at this location. So if this was y equal to f2 of x, the top function, and the bottom was y is equal to f1 of x, when I subtract these two, so when I write f2 of x minus f1 of x, that would be the height that I am after here, this height. This is the height of the rectangle. Well, if I take the height of the rectangle and then multiply by the base of it, so if I multiply it by the base dx, that's going to be area of the strip. Now I want to add up all these areas from the very left strip that I have to the rightmost strip that I have. So how do I indicate summing all of these things? So, okay, sum all of these things from, so integral indicates a sum. We have a starting point, whatever our starting point is and whatever our ending point is. So it goes from A to B. Well, f2 minus f1 is like high minus low here. That itself can come from integral of a differential, meaning if I go a small displacement, another small displacement all the way to the top boundary, the sum of all of these displacements will be f2 minus f1, just like d minus c over there. So here I go and say this area, the area I was calculating in this fashion in Calculus 1, the area between two curves was written like this. I modify it to the following just to prepare for more advanced topics. I say this inner integral is really integral of the dy from the lower boundary of f1 of x to the higher boundary of f2 of x. So all of this will be that, because integral of dy will be higher value minus the lower value. And then the rest of it will stay as before, so it's going to be dx. So in this kind of graph, which we call it vertically simple, our strips are going in a vertical direction. We have integral of dy to go in a vertical direction first, and then integral with respect to x, which means we are sweeping from left to right. Let's go repeat this whole thing all over again, just to be as a matter of practice. Let me redraw this thing again. Okay, I want you to do this one yourself. Okay, so what you want to do, so our deal was that we pause this thing and then you try to go through the same reasoning, exact same thing that I did, but now for the second graph we had, which was horizontally simple pictures. Let me draw it maybe. So what we are going to do is to justify this second approach to calculating the areas. So in this case, perhaps x is given in terms of y, and our flat boundaries are y at c and y at d. So this one is going to be referred to as a horizontally simple. So the terminology in your text is called, this is horizontally simple picture. So I have some function, in this case x is given as a function of y. The one on the right we call it g2, and the one on the left we call it g1, or whatever you want to call it. So in this case we are going to choose to, for the first round, we are going to have these differentials that's going to go from the left boundary to the right boundary. Okay, so as I go from left to right, each of these things is a differential of x. Is that right? This is differential of x. What is my starting point? My starting point is from g1 of y, meaning what? Meaning here I had some x, and my starting location here as a function of x is as a function of y, this is y of course, as a y function, the starting value as a function of y is g1 of y. So that means this x here is a function of y, and that's what we refer to as g1 of y. So this is g1 of y. And then we go as far as this location, which is our terminal point, and that is g2 of y. So sum of all these differentials from the left to the right, so from g1 of y to g2 of y, is going to be the width of this rectangle. So I have a rectangle here. I'm calculating the area of it. So the height of it is going to be this, and the width of it now is this differential of y. So now I take that and multiply it by differential of y. So all of this is simply g2 of y minus g1 of y. So that is this dimension of the rectangle, and the narrow direction is dy. When I multiply it, I have the area of that strip. The strips start from the very bottom here, wherever that is, and in our notation we call the starting value c. So we are starting from c to the very last stop, which is going to be perhaps called d, and then we have our last contribution from the strip over there. So the second integral goes from c to d, and then integral of g1 of y to g2 of y of dx dy. So notice how different the setup is. This one goes with dy first and then dx. This is dx first and dy. Again, we need to understand exactly what is involved, because when there is dx, dy, and dz, there will be essentially 6 different ways of writing this, and it would be a Herculean effort if you try to memorize it. They're all going to sound like each other, and it would be impossible essentially to do that. Instead, what you want to do is to understand how you are setting the whole thing up, how you are sweeping the area. Think literally in terms of slicing like a loaf of bread or something, and in which direction you are slicing it, and how to set up all of these integrals, and that's going to be the key to success. Okay, let's go ahead and do some basic examples to become familiar with this thing, and quickly we are going to go after problems that are going to be substantially more complicated with more ingredients in it. So at the beginning, most of the problems we do are very similar to what you have done in Calculus 1, just that the notation has changed, the way we approach it has changed. So suppose I want to calculate the area of the following shape. So I have, say, a parabola here, and we have this parabola. Let's call it say x equal to y squared, and then we go as far as say this point, this final point. Suppose this is x of it is say 4 and the y of it is 2. Let me clean this. So what we are after is write this area as a double integral. Okay, write it as a double integral or as an iterated integral, and then, well, also calculate it. Okay, how do we approach this? Well, let's again emphasize that we want to write the area as a iterated. Write the area as an iterated integral, and evaluate it. Well, we always have a choice of these two approaches that we had here. We always have a choice. Sometimes one choice is a lot easier than the other one. Sometimes both of them are available and equally simple or equally complicated. So what are our choices? Our choices is how we slice this and how we sweep it. So let's see. Let's try both of them. We see what happens. So suppose this was a loaf of bread and I'm slicing it this way. Before we go any details, well, what was my other choice? Let's just set that up as well. At least conceptually, it's just as easy to take the same loaf as we had before. Okay, so this is what we are after, and the way I stack things, maybe I slice it this way. So horizontal and vertical. Well, then we go after one of these slices. Okay, suppose here's my slice. I want to go after that. What do? I calculate the area of that, and then stack all the slices next to each other and add them up. So what do? I say, well, I choose a certain x at which I'm doing the slicing, so I could have chosen any of these things. So my slice is indexed by x, by the location where I actually did the slice. Okay, so as I go up, in this slice, to figure out how long the slice is, I am adding differential of y's here. So it's differential of y. So my displacements are in the y direction. I start with dy. Well, I have to have a lower curve at which I start and a higher curve at which I end. Lower curve is what? Lower curve, so at this case I am starting at y equal to 0. In this case my function is y equal to 0. And then I go as far as, well, where do I stop? I stop at, well, my function is given as x equal to y squared. I can convert it to my stopping place. I can write this thing as y is equal to square root of x. So my stopping place is going to be square root of x. Okay, next I say my slice is my leftmost slice in this picture start at 0 and goes as far as 4. So I'll take this height. This is the height of the rectangle multiplied by dx. So when I take the height multiplied by dx, I have the area of that particular slice. My slice starts at x equal to 0. The leftmost is x equal to 0. Then I stop at 4. And this is going to be my my area. Let's go ahead and calculate this. So integral of antiderivative of dy is 1 between radical x and 0. That is simply radical x minus 0. That is how tall this strip is. This cut is radical x. I have to multiply that by dx. That's going to give me the area of that little slice. And that integral has to be calculated from 0 to 4. Well, let's rewrite this thing. 0 to 4, you can write it as x to the power of 1/2 dx, and then that's going to be x to the power of 3/2 divided by 3/2 between 0 and 4. And here's another way of writing 2/3 of, this is x radical x if you wish, between 0 and 4. So this becomes 2/3 of 4 times radical 4, that's 8, and at the bottom is just 0, so all boils down to 16/3. So what did we do here? I needed to know what is my stopping place at a chosen value of x at which I'm cutting. When I start at x, where do I stop? Well, the height of this strip is going to be given in terms of my starting location as radical x. Now let's go to approach number 2. Approach number 2, we said we are going to slice this thing from left to right. So the strips that I'm looking at would be something here. Let's take a pick one of them, see how does this look like. So in this case we say we choose certain y. At that y we make a slice. At that y I need to know where I start my slice and where I stop. Well, the starting location of this slice is given to us straight out, x equal to y squared. So the location at which this slice starts is x is equal to y squared. At what point do I stop? Well, all of these things are stopping at x equal to 4. So how long is this slice? Well, it's 4 minus y squared. How can I write that? So I say I start at y squared. I go as far as 4, and my displacements are horizontal. They are all dx's. If I take all of this, which is how long this slice is, and multiply it by dy, so dy is how thick this slice is. I take that, multiply by dy, and my y starts at the lower value of 0, and the highest value of the y is 2. So my outer integral goes from 0 to 2. Okay, now I'm ready to do this thing. I say 0 to 2. Antiderivative of dx is 1. Between 4 and y squared, this simply becomes 4 minus y squared. That is simply how long that slice is. And then I'm multiplying by dy, which is the thickness of that slice. The integral of 4 minus y squared, integral of 4 is just 4y. Integral of y squared is y cubed third. And then I have to evaluate this thing between 0 and 2. At 2, I replace it, get some numbers. At 0, I'm going to get all zeros. So 4 times 2 is 8. 2 cubed over 3 is 8 third. And at lower end, I all have zeros. I take my common denominator, becomes 24 minus 8. And I recover the same answer, 16 third, that I had here. I have it here as well. So once again, this is the problem you have done in calculus 1. Area between curves is nothing new, but the way we are doing it is different. We are writing as a iterated integrals. We have two integrals to compete. Okay, sometimes the problems that we deal with for writing the area, one of them is a lot easier than the other one. Sometimes one of them might be essentially impossible to do, while the other one is easy to do. So even though in this case both approaches rather easily gave us the same number, sometimes we have to be smart to pick one of them and go after that first, as opposed to wasting time with the other one, which might not be as straightforward. So let's take a look at some examples where one approach could be easier than the other one, or at least see how so here's an example. We are given a parabola as a wall of a region. Parabola, say y is equal to 4x minus x squared, and we are given another wall y is equal to minus 3x plus 6. And then we have another wall, if you wish, which is just our x-axis, or y equal to 0. And the question is, well, what is this area? Well, however we want to approach this problem, it's going to be a bit more complicated than what we had before, because it's not a vertically simple or horizontally simple type of a picture. So the way we are going to approach this is some method of a divide and conquer approach. One thing we can do is to split it into several pictures where each of them is one of these styles, and then apply that method to it. So one approach we can have here is to start a cutoff in this. So here I split this problem into two problems, and then I say, okay, let's handle the left part in one integration and approach the right one in another one. So here is going to be so in this case I have to make a compromise. First cut it up into pieces, and then I still have a choice, but it looks a lot easier for me to slice this up in this direction and be done with the problem quickly. So how do we approach this? Well, what's the complication of it? The complication is that the lower function on the left is something, on the right is something else. That's why we split the problem into two pieces. So how do we write this thing? It says, okay, on the left part of my integral, okay, I'm going in the vertical direction first, so it's going to be dy. The starting value is minus 3x plus 6. The ending value is 4x minus x squared. So that's going to be how tall each of these strips are going to be, the difference of these two. When I multiply by dy, I'll find the area of that strip. Then my x, the leftmost point, is going to be this location, and the rightmost point is going to be wherever we drew this line. So how do I find these two? Let's go after this one, which is easier. This one is wherever my line cuts x-axis. So I say y is equal to minus 3x plus 6. The x-intercept of it is where y becomes 0, so x becomes simply 2. So the ending location here is 2. How about this starting location? Starting location, well, is the intersection of these two curves. So how do we find it? Well, we set the two curves equal to each other to find their intersection. So I bring everything to the right, so it becomes x squared minus 7x plus 6 is equal to 0, and this one factors as x minus 6 times x minus 1 is equal to 0. So that tells me either x is 6 or x is equal to 1. Well, x equal to 6 is going to be some intersection, so this curve parabola goes down and this other line cuts it further down. So x equal to 6 is not what we are after, rather is a starting value which is just 1. So this is how tall each strip is, and then when you multiply by dx, you're calculating the area of each strip, and then from 1 to 2, that's going to be the green portion. How about the red or purple portion? Can you write that for me? So again, I encourage you to go ahead and write the second piece and then come back and continue. So the second piece, how does it go? We are still cutting in a vertical direction, but my starting value is from 0. My ending value is still 4x minus x squared. We are going in the y direction. That's how tall each strip is. And then from now our starting location is 2. Ending location, well, what's the ending location here? 4x minus x squared. We set that equal to 0. 4 minus x times x equal to 0. So either x is equal to 4 or x equal to 0. X equal to 0 is start of this parabola here, and 4 is where it ends. So our right piece goes from 2, this location 2 to 4, and each of these heights has to be multiplied by dx to get the area. So of course the formula is not written with so many parentheses, it's already crowded, so we have to understand what is meant by this. Minus 3x plus 6 to 4x minus x squared. This is going dy first, dx, and the second piece going from 2 to 4. Inner integral is from 0 to 4x minus x squared. This one goes dy and then dx. So that is the area. Once again, it's the exact same problem that you would have had in Calculus 1. Just the style of writing is different. So antiderivative of dy is y, so this area becomes integral from 1 to 2 of. We go after this. Antiderivative of dy and antiderivative of 1 with respect to y is just y. We have to calculate this thing between the lower value, which is minus 3x plus 6, to the higher value, which is 4x minus x squared. Once that is done, we still have another integral to do. And then there is a second half of all of this from 2 to 4. Same thing, antiderivative of dy with respect to y, of course, is y. It's between 0 and 4x minus x squared, and then integral dx. So let's write 1 to 2. I have to subtract these two, so I get 4x minus x squared minus 3x plus 6, all of this dx, and another half. 2 to 4, y has to be replaced by 4x minus x squared, then minus 0, all of that dx. Well, I'm sure you can finish this problem, but let me just quickly write it out. So I'll have integral from 1 to 2 of this is going to become 7x minus x squared minus 6 dx, and then 2 to 4 of 4x minus x squared dx again. So this is going to be 7x squared over 2 x cubed over 3 minus 6x between 1 and 2, and this is going to be 2x squared minus x sorry 2x minus x cubed over 3, and all of that between 2 and 4. So some arithmetic, those basic calculators with 3-line display can help you do this thing, or just do it by hand. So at 2, this becomes 4 over 2 is 2, becomes 14, minus 8/3 minus 6. At the 1, it's 7/2 minus 1/3. I made a mistake here. And then here at 4, we get 2 times 16 is 32 minus 64/3, and then at 2 I'll have 8, and then this becomes 8/3. So we might as well simplify a little bit and then add up all the pieces. So I'll have this is 2 minus 8/3, and then I have minus 7/2 plus 1/3 minus plus 6, and then I'll have here 32 minus 8 minus 64 third plus 8 third. So I try to collect similar fractions to with each other first, and then add up the other pieces. So let's do it like this. 2, 6 is 8, and 8 cancel each other out, and 32, so I have 32 here. All the fractions with a denominator of 3, let me collect them all at the same time. So I have minus 8 and a 1, and then minus 64 and an 8. Let's put them all together. So that took care of these 4 items, and then I have a 7/2 left over. So hopefully we haven't missed anybody. And what we have, so again, these two cancel each other out. This is 63, so I'll have 32 minus 21, and then minus 7/2. Okay, so I'll have 9 minus 7/2, and if I am not mistaken, perhaps I am. Let me double check my calculations to see if run it again. 8 and 8 and 32, so I have a 3, 8, 1 minus 64 plus 8. Oh well, sorry for that, another mistake here. Of course, 32 minus 21 is 11, and okay, that was embarrassing. So 15/2 becomes my the area calculated in this style. Okay, did we have another option? Well, yes, we always have option. The question is it easy or wise to actually apply it? So let's go ahead and redraw this picture and see what was my second option. So I had something like this. So can I slice this thing horizontally? Yes, you can slice any which way you want. What would be our obstacles here? Obstacle number 1 is, well, we have to find this location, because the starting on the left here we have this function, and here we have this one. Well, that's not a major obstacle. We can find that split point, and just like the previous approach, we can go ahead and calculate this one in 1/2 and calculate this one in another half. So that is so far conceptually no problem. Well, next we have to figure out what is our function as x in terms of y. So here's x is equal to g2 of y, and here x is g1 of y. I need to find these functions with respect to this straight line. That's not going to be a substantial obstacle, because what I had here was y is equal to, I had y, the equation of this one was given as y is equal to minus 3x plus 6. Well, this is easy to rearrange. You can write y minus 6 is equal to minus 3x, divide by minus 3, so become x is equal to y minus 6 over minus 3, and you can write this thing as 2 minus y third. So I can start this thing at x equal to 2 minus y third if I want. Okay, well, how about the left or right of this blue curve? So we need to do the same thing for this one. What was the equation of that one? The equation of that one was given to us as y is equal to 4x minus x squared. It was given as y is equal to 4x minus x squared. The question is, I want x in terms of y. Well, this is going to be a bit more work. It's doable in this problem, but slight variation in this problem, we would not have been able to, so luckily, actually figure this out. X in terms of y, I can bring everything to one side. X squared minus 4x plus y equal to 0. Apply the quadratic formula here. Say x is equal to minus b, that's going to be 4, plus or minus b squared minus 4a times c, that is minus 4y, divided by twice the a. So we are applying the quadratic formula, except that instead of a number here I just have a y. So I have two answers. One is, let's write it like this, 4 plus radical 16 minus 4y over 2, and the other one is 4 minus radical 16 minus 4y over 2. We can make it a tad bit simpler, factor a 4 out of this and bring it out. It becomes 2 plus radical 4 minus y. This becomes 2 minus radical 4 minus y. Okay, so there was a bit of work involved in this one, and then I can say this is the right half, this is the left half. Well, of course, the right one is the one with the plus, 2 plus radical 4 minus y, and this was 2 minus radical 4 minus y. So you see the work is increasing. We are adding up the work we have to do. So once we have these, then we have to actually write the integral from the left to the right and do it that way. So what else is left to do in this case? We have to figure out what is this intersection. We had the intersection of the two curves. We didn't need to do it before, but now we do need to do it. So we had one curve, y is equal to minus 3x plus 6, and the other one was y is equal to 4x minus x squared. That intersection comes out at 4x minus x squared is equal to minus 3x plus 6. I believe we did this before. X squared minus 7x plus 6 equal to 0. So x minus 1 times x minus 6 is equal to 0. So one intersection was at x equal to 1. And if x is equal to 1, y becomes 3. The other intersection we said previously it is not relevant to us. At x equal to 6, our y would have been minus 18 plus 6 is minus 12. That was the intersection we said it is falling down here. It's not relevant to our problem. So the location of this is at the location is at x equal to 1, y equal to 3. That is okay. So that took a while. Now we have to actually write down the integrals for the green and yellow portion. By now you notice that this is just layers upon layers. So if you had started this approach, you might have wised up in the middle that it's better to go in the vertical direction. But just to complete this thing, let's go finish it up. How do I write the integral? I write the integral, so going in horizontal direction, I write dx first from the left, which is 2 minus y third, all the way to the right half, which is 2 plus radical 4 minus y. And then the green region starts at y equal to 0 and goes as far as y equal to 3. So that's dy. That's the green portion. Let's just and then to that we have to add another piece, the yellow piece. The left and right of it are two sides of this parabola. So it starts from 2 minus radical 4 minus y to 2 plus radical 4 minus y, and that with respect to x. And then with respect to y, we have one more obstacle. We are starting at 3, but where do I stop there? So what do you think? What should I write for upper value of this integral? That is, perhaps you want to pause this thing and think about it and then come back with an answer. So I start at 3. Where do I stop? Well, that's the highest value that I have there, and highest value, I leave it to you to think about it. The highest value will be 4, or if you want to work it separately, if y is 4x minus x squared, what's the highest value of y? So I calculate y prime is 4 minus x, 4 minus 2x, set it equal to 0, x becomes 2. When I take it 2 and plug it here, y becomes 8 minus 4, and that's going to be, 8 minus 4, and that would be a 4. What that means? That means the highest point of this picture is the point with coordinate 2, 4.